Okay guys, we'll start with the end of 5.2 and then we'll go on to 5.3. They're really similar, they're really closely tied together. We already went over 5.2 on Friday. Alright, so here's the big picture idea. Okay, this is number 68, and we'll do it in more detail in a second. But here's the big picture idea. This is what you're really doing. Maybe not big picture, maybe this is the why. What we're really doing is taking this entire parentheses, just like we've in the past distributed in a number or distributed in a term like 2x. Instead, we're going to distribute in this parentheses to each term. Because parentheses mean it's a group, you treat it like one term. Okay, so what this is really saying is x plus 2 times x squared plus x plus 2 times x plus x plus 2 times 5. Right, so after we distribute in that parentheses, and this is not how we're going to do it, I'm just showing you the why. Then we're going to say, oh, well, this is easy. We've done this, right? This one we just multiply in the x squared, we multiply in the x, we multiply in the 5, and what we get is x to the third plus 2x squared plus x squared plus 2x plus 5x plus 25. So the big picture, or the what, or the why is, so essentially what we're really doing here is we're taking every single term from the first polynomial and every single term from the second polynomial and multiplying together every possible combination. And I'll give you some general steps next. What that means is I combine this x with every single thing in here. I combine this 2 with every single thing in here separately, and so I should get 2 times 3, a total of 6 terms. Right? So I multiply x squared times both of these. I multiply x times both of these. I multiply 5 times both of these.
Is it plus 10 at the end? Or am I wrong?
Yeah, it's plus 10. There we go. Easy peasy. Okay? You could think of this visually. Okay? I don't usually show people this, but why not? Okay, this might confuse some people. Some people are very visual, spatial. So I'll just show you, for example. Let's talk about this in terms of area of a rectangle. Okay, if I have some length x and some length 2. So this side, total, is x plus 2 long. Okay? This might be hard for some people to grasp. If you don't grasp it, whatever. On the other side, okay, let's take some length and say this is length x squared, this is length x, and this is length 5. Okay, so total, this side is x squared plus x plus 5 long. right? So we could write this area in two ways. We could say the area is length times width, or it's x plus 2 times x squared plus x plus 5, okay? But that's also equal to the area is the sum of its parts, right? We could just add up all of its parts. So we could say the area is, and what's the area of this?
X times x squared,
Yeah, so x to the third. And this one?
2x squared,
Yeah, and this one?
2x,
Yeah,
x squared, 5x,
yeah.
10.
And look at that, what the heck? What we did is, we multiplied every possible combination and get this exact sum. So what we did is we combined x with every single thing from the other polynomial. We combined 2 with every single part of the other one, and we get x to the third plus x squared plus 5x plus 2x squared plus 2x plus 10, and then combine like terms, which is x to the third plus 3x squared plus 7x plus 10 after combining like terms. So just trying to give you a couple ways to look at this. One is we followed our same distribution rules and just distributed the entire parentheses, right? Then it's nothing new, okay? Another way to think about it, visually finding the area of a rectangle where this is one side, x plus 2, and this is the other side, okay? And now I'll give you the general steps that I like to follow. Actually, let me just mention one more thing. Now, let's do the general steps first, and then I'll mention that one thing. Okay. And I'll use the same example problem. 68, which is x plus 2 times x squared plus x plus 5. Okay. So I'm trying to use as simple a vocabulary as I can while being mathematically accurate. But you take the first term of your first polynomial and you distribute it to every term in the next parentheses, regardless of how many there are. If there are 7 things in the next parentheses, you multiply it by 7 things in that parentheses. In this case, there were 3. So step 1 gives us x to the third plus x squared plus 5x. Okay, and then we add on. And step number 2 says, take the second term. And everything else is the same. Okay, so we take the second term and we distribute it into everything, so I'll do that one in purple. So step 2 here gives us positive 2 distributed into everything in the second polynomial. So this gives us plus 2x squared plus 2x plus 10. And then step 3, which isn't here and won't show up that often, is repeat with, whoops, every term in the first polynomial if there are more than two terms. Right, so if there was a third term, and a fourth term, and a fifth term, you would continue the same pattern. You would distribute it into everything. Distribute the next one into everything. Distribute the third into everything. And a big part of math is when I say combine every single one of these with every single one of these, you do it systematically, logically, from one beginning to one end. You don't just go, 2 goes with this one, and a 5 goes with that one, and that's just a place where that scattered nature means you lose one in the process, or you count one twice by accident. So anytime I come across a situation like this, where you want every possible combination, which happens a lot in probability and statistics with polynomials, I start at the first, and I go 1, 2, 3, 4, 5, then I go to the second, and I go 1, 2, 3, 4, 5, right? And I do that systematically. So the next term is real straightforward, just combine like terms. Okay. And that's it. So step 3 over here, I'll do in red. Is I get x to the third plus 3x squared plus 7x plus 10, because I combined my like terms here, just being x squared and x squared, x's and x's. Okay. Now let's do a problem like that, and then I'll bring something up. Okay. So here's another example just like that. Let's do 64, starting out with an easier one. So we get 3x minus 4 times x plus 5. Okay, I'm going to take my 3x, distribute it into each of these. Then I'm going to take my negative 4 and distribute it in as well. So 3x times x, 3x squared. 3x times 5 plus 15x. Negative 4 times x, negative 4 times 5. And then finally I combine my like terms, and I say I've got 3x squared plus 11x minus 20. Now, just to bring something up, we'll do a couple more examples. Okay, but to bring something up here is FOIL. A lot of you heard FOIL in the past. FOIL stands for first, outer, inner, last. And I would say this is a terrible way to remember this. It isn't, but it's a terrible way to memorize multiplying polynomials, right? What's its big limitation?
Only 4 terms?
Yeah, exactly. You can only use this for binomial times binomial. That's it. Right? It doesn't work when you have 3 terms. So we could use it on 64. Just to do a quick example like that, we could FOIL a problem like 56. So x plus 4, x plus 6. So we could FOIL this. I always think learning one big general step or general process is way better than learning a bunch of small, detailed, memorized ways. So FOIL would say, do your first, then do your outer, then do your inner, then do your last, going FOIL. Okay? But that's the same as saying distribute the x to both of these, then distribute the 4 to both of these. So it follows the exact same logic, and you don't remember one special circumstance for one special product. Okay? Same as x plus 4 times x plus 6, and just saying this times both, and so you get x squared plus 6x plus 4x plus 24, regardless of which way you did it. Combine your like terms, x squared plus 10x plus 24. Okay, I'll do another example or two, but I just want to highlight one other small detail. The way you write math can lead to mistakes, and I told you one of those like in the first chapter, when people say 5 plus 1 times 6, I can see by the way they wrote it that they're probably going to do addition before they do multiplication just by their spacing, and I can see that's going to lead to an error. Same thing when people do distribution and you have, well, let's just say we're distributing 5 into x squared plus 2x plus 3. You shouldn't be saying I'm sending this 5 in to all 3. What I mistakenly see people do, I don't know who they learned this from, but they mistakenly say the 5 goes like that. And then to me that's super misleading. I mean, just visually, spatially. This is saying the 5 is going to the x squared and somehow either the x squared is going here or the combination of 5 and x squared is going here. Because I mean, you clearly have an arrow starting here and going here. And I would just say that's one of those things that if you write it that way, it's going to cause even one extra mistake one time in your life, but realistically lots more than that. But I would just avoid it. And this is what you're really doing. Visually, you're sending a 5 to here. Then you're starting back at the 5 and sending it to here. So I totally misrepresented. I mean, that serves no purpose other than to mentally confuse you. Okay, so let's do a couple examples, then we'll talk about 5.3. All right, let's do a harder one. What about after 68, one like 70? Okay, 70 is y minus 2 times y squared minus 4y plus 3. So, somebody help me, what would we start with?
Take the y,
Yeah, take the y, and?
multiply by each term and then,
Yeah, and so what would we get?
y to the third power
Yeah,
minus
4y squared?
no, 4y, because we're multiplying, not adding, right? So yeah, so 4y squared, and then? Keep going.
3y.
Yeah, plus 3y, perfect. And then, to be the same person or other people, what would we do next?
Take the negative 2, do the same thing.
Negative 2, not 2, and do the same thing. And so what we get?
Negative 2y squared
Yeah,
plus 8y
yeah,
minus 6.
yeah, exactly. And that's the hard part. After that, it's just combining terms. So it's y to the third. I would say here's some y squared and y squared, so minus 6y squared. Here's some y's and some y's. So I've got 11y and then minus 6. Okay. And that's going to work for multiplying any set of polynomials you multiply. Okay? 5.3 is a special case, not that it's different, but just because it shows up often enough that you could realize the shortcut. But absolutely you could use these general steps on every problem without any exceptions. There's no asterisks. What if you divide by 0, right? You're not dividing. So there's no asterisk. Every single polynomial you multiply like this. Okay, no exceptions. Last one, let's do 74 because we can always step it up a notch. What if there's 2 times 4 of them? Oh, and we can even step it up a notch more. This is good. This is 2 things times 4 things for a total of 8 possibilities. that's good. It's not quite where we're gonna go, but okay, what will we do first? Somebody other than Zach, you'll be on the last one.
Same thing, we just do it x multiplied by x3 will be x4, and then plus
So what we get? The x to the fourth plus?
4 plus 4x cubed,
Yeah.
and then multiply this will be 7x squared,
Yeah.
and 3x.
There we go. And then?
Wait, are there next terms?
Oh, not yet, we gotta distribute the second one.
Oh,
Multiply the 1. But that doesn't change anything, so really it's just saying write it all. So, plus x to the third plus 4x squared plus 7x plus 3. Then you combine the like terms. So we got some x to the thirds. We got some x to the squareds. We got some, use my different shapes. Got some x's. So we got some circles add up to 5x cubes, rectangles add up to 11x squared, and 10x plus 3. Right? And then I'll give you guys one last problem. We'll finish off the section. I'll have you guys do it on your papers, see if we come to the right answer. So the culmination here, then, we'll step it up a notch. What if on 78, what if we now have 3 of them times 3 of them, so we have 9 possible terms, right? So why don't you guys do that, whoops, on your paper, then we'll do it together, and then we'll do 5.3. Okay, let's do it together. So, what do we do first? Let's see, Cindy, yeah, help me out, what do we do here?
The 2x with the 2x? Or,
Oh, you mean x squared?
yeah, the x squared.
Yeah, definitely different than 2x. But yeah, x squared, and x squared, and?
Then x squared with negative 2x,
Yeah.
and then x squared with negative 1.
Yeah, so we get x to the fourth minus 2x squared minus x squared, and then, whoops, that was x to the third, phew. And then,
And then 3x with negative 2x.
well, we gotta start at the beginning.
On-
You gotta multiply it by every single one, we have every combination. So first we have to multiply the 3x by, oh, you said 2x, but I think I
Yeah.
meant x squared.
Oh yeah.
Gotcha, I thought you
Yeah.
meant 2x. Okay, so yeah, first with x squared, then,
And then with negative 2x,
yeah.
and then with negative 1.
Yeah, so we get plus 3x cubed plus, whoop, minus 6x squared minus 3x. And then,
And then the 1 with x squared,
the 1 with x squared,
and then with the negative 2x, and then negative 1.
yeah. So we get plus x squared minus 2x minus 1. You could line these up vertically if you want. The reason I don't do that is because it doesn't always work, and I don't like, yeah, again, I don't like teaching people like 3 different methods and then people trying to remember which is which. Okay, so we got the x squares all by itself, then we got some x cubes with some x cubes with no others. Then we got some x squareds with some x squareds with some x squareds, and finally we got some x's with some x's. So combining unlike terms, we get x to the fourth plus 1x cubed. Minus 7 plus 1 is minus 6x squared. And then minus 3 of minus 2 is minus 5, minus 1. So hopefully everybody got that.